Okay, we're continuing our discussion of sound, and we were speaking about the speed of sound in the last video, and in this video we're going to introduce the idea of intensity. So sound waves can, just like any other type of wave, can transport different amounts of energy. And the way to think about this when we look at energy transported by a wave, let's say we've got a rectangle, like a window or something like that. We want to know how many sound waves or how much energy per unit of time, and energy over time is power, basically how much power goes through this window, goes through this rectangular area. So that's why the units for the intensity of sound wave are watts per meter squared. We're thinking of how much power travels through this window carried by a sound wave. So you can see on this chart here varying degrees of intensity. So the threshold of human hearing, the softest sound that we can hear, has an intensity of 1 times 10 to the negative 12th watts per meter squared. And that ranges all the way up to, on this chart at least, a jet plane taking off, which is very intense, has an intensity of 100 watts per meter squared. Another way we can measure the loudness or sound level of sounds is on the decibel chart, or using units of decibels. And it is decibels are based on the threshold of human hearing. So something with that has a decibel level of 0 is right at the threshold. Like the softest thing you could possibly imagine would just be just over 0 decibels. And that same jet taking off is 140 decibels. And then you can see, of course, all the things in between. So loudness, the loudness that we can hear, and what we perceive as loudness or volume, is related to intensity, but they're not exactly the same. So there's a proportional relationship here, but they're not the same thing. So we need to be careful to distinguish between intensity and loudness. So the way we do that, the way those two things on that chart are related to each other, is that the intensity, which we're going to represent with the Greek letter beta, and the units of that are the decibel, named after Alexander Graham Bell, I believe. That's Alexander Graham Bell. So beta is equal to 10 times the log base 10, of the intensity of the sound divided by this intensity sub-0, this intensity naught. That is the threshold of human hearing. So this is really a constant. This term right here in this equation, this is always going to be 1.0 times 10 to the negative 12th. And the units of that are watts per meter squared. So really the only variable on this side of the equation is the intensity of the sound. And so that's what relates the intensity and the loudness. So this is intensity. Then over here on this side of the equation, this is loudness. So they're not exactly the same, but they are related to each other. The higher the intensity, the higher the loudness. But it's not just a simple one-to-one relationship. So let's calculate this relationship between intensity and loudness. Let's say we have a busy street corner that has a sound level of 75 decibels. What is the intensity of that sound? Well, our equation said that the loudness, beta, is equal to 10 times the logarithm of intensity of whatever it is we're investigating over the intensity at the threshold of human hearing. So this is the variable we want to solve for. We want to find intensity. And so we can start by dividing both sides of this equation by 10. So beta over 10 equals the log of I over I naught. And then this is where a lot of people might get stumped because of algebra. How do we get rid of this logarithm? Logarithms are not something we use very often, and so although you've probably learned this in the past, you've probably forgotten how to get rid of a logarithm. The way you do that is you take 10 to the power of whatever is on that side of the equation. So 10 to the power of log of I over I naught equals 10 to the power of beta over 10. And so the 10 to the power of and the logarithm will cancel each other out. And on this side, I've got 10 to the power of beta over 10 equals those things canceled out, and I'm just left with I over I naught. So then if I just multiply both sides by I naught, I've got I naught times 10 to the power of beta over 10. That will equal the intensity of the sound. So what was the loudness? Beta, 75. What is the intensity at the threshold of human hearing? That is, what is that? That is 1 times 10 to the negative 12. Sorry, I was kind of peeking at my notes on the next slide. So 1 times 10 to the negative 12 times 10 to our loudness again is 75. Beta is 75 over 10. So this is our I sub naught. That was our loudness, 75. So 1 times 10 to the negative 12th times 10 to the power of 75 over 10 equals our intensity, and that is 0.00032. After all, we are limited to 2 significant figures here. So we put that into scientific notation. That would be 3.2 times 10 to the negative fifth watts per meter squared. That's the power of that wave going through a 1 meter square. Just, I think this is a good way to visually think of intensity. We're talking about the power carried by that wave through a 1 meter square window. Think of it that way. Okay, so I was able to solve all of that problem on one slide. I didn't need the second slide here. Okay, so here's the thing. Because loudness and intensity have this weird relationship, they're not. It's not a one-to-one relationship. What we see is that doubling the intensity does not double the loudness, which you might think it would, but it in fact does not. And we'll go through an example problem here in a couple slides to show this. But what happens is that actually doubling the intensity really only results in an increase of approximately 3 decibels. The other thing about sound is it diminishes with distance. So we talked about this in the last chapter when we were talking about waves. The farther you get away from the source of the sound, the less loud it seems, right? If you are right next to a jumbo jet taking off, that will be incredibly loud. It will probably cause physical damage to your body. But if you are 100 yards away, it's not as intense. If you're a mile away, you might not even hear it at all. So the relationship here is that intensity is proportional to 1 over r squared, where r is the distance between, let's draw our little airplane here, taking off, and you, the person hearing it, the distance between you and the source of the sound is r. So if you, let's say we've got, oh, why did I draw an 8? I don't know. This stick figure is a little fatter, I guess. So if we've got a distance here for this guy that is r, and this one is 2r, doubling the distance you are from the source of the sound would be r squared. This guy would actually only hear 1/4 the loudness that this person has. So if you double your distance, you actually cut the loudness by 4, by a factor of 4. Okay, so I'm going to try to finish up this example problem before I run out of my 15 minutes. So a trumpeter plays at a level of 75 decibels. So we've got one trumpeter, he's playing with a loudness of 75 decibels. Let's say we have 3 other equally loud, I can't believe I missed this typo, loud, not loud, loud trumpet players that are going to join in. What is the new sound level? Well, you might think, well, 3 more, you're going to end up with 4, so it'll be 4 times louder, but that's not the case, is it? So even if we add 3 more trumpeters, we're not going to quadruple the loudness. What is actually going to happen? Well, if we work through the numbers, the loudness, beta, is equal to 10 times the logarithm of the intensity over the intensity at the threshold of human hearing. So that's going to be equal to 10 times the logarithm. So by quadrupling the number of trumpet players, we do quadruple the intensity. So this is going to be 4i over I naught. And then even I'm a little bit rusty dealing with algebra with logarithms. It's just not something that comes up all that often. So what this is equal to, when you've got a number like the 4 up here, we can factor that out of the logarithm by taking the log of it separately. So we've got log of 4 plus the log of I over I naught, I think. Okay, so that's equal to our loudness beta. So we then have to distribute the 10 here, and this is equal to 10 log of 4 plus 10 log of I over I naught. So this we can put into our calculator. 10 times log of 4, that gives us 6.02. And if we add to that this is just the intensity of one trumpet player, and that was given in the problem statement. The loudness, this equation here, 10 times log of I over I naught, would be the loudness of one trumpet player. Well, that was given in the problem statement as 75 decibels. So if we add them together, I guess this should only be 2 significant figures, shouldn't it? Let's forget that 2. Let's call it just 6.0. If we add them together, we get 81 decibels. So by quadrupling the number of trumpet players, we went from 75 to 81 decibels, which is probably not as much as you would have expected. Now, a quicker way we could have done all this, forgetting all this logarithm stuff, is to remember that if you double the intensity, that leads to a decibel of plus 3 decibels. So if we had one trumpet player and we doubled it, we would have gone from 75 to 78, and then we've got 2 trumpet players, and if we double that again to be 4, then we add 3 more and end up with 81 decibels.